Hi, everyone. My name is Cindy Schmidt. I'm based in California at NASA Ames Research Center in the San Francisco Bay Area. And both my colleague Amber McCollum and I are really excited to bring you this series on remote sensing for tribal lands. The way, I don't want to spend too much time talking here because we have a long session today. It is probably the longest of all of them, just a heads up, because the first one is always quite long. But the way we're going to do this is we have recorded all our sessions, but even though we've recorded them, both Amber and I will be online to answer your questions, any questions that you might have that you can post in the question box. And so at the beginning of the session, we're going to give you an introduction, and then there will be an overview of a tribal location in the U.S. Today, we're going to give you some information about the Navajo Nation, and then we're going to jump right into a lecture, and then following that, we're going to have a hands-on exercise. For those of you that are looking for continuing education credits, Amber has posted the link on where to get the form in the chat box. And that will also be available on the United Tribes Technical College webpage. It's not there yet, but it will be soon. Also, there will be some homework for you to complete. We'll make a link available to just a Google Doc at the end of every session. And the homeworks aren't actually due until the end of November. So you have time to go through the exercises at your own convenience and then do the homework. And then once you turn them in, you'll either get a certificate of completion, and then if you're interested, also continuing education credits. So if you have any questions about that, please don't hesitate to ask us. We'll give you our emails, and then you can also ask questions here at the end of the session. Because we'll open it up to questions at the very end. So we're all really happy you could join us. So this will be really fun and exciting and very new for us. And I wish we could do it in person. I wish I could meet you all in person, but it's maybe next year. Maybe next year we'll plan that. So at this point, I'm going to jump over to let you say hi to Amber, and then we'll jump right into our session. There's Amber. Oh, can't hear you, Amber.
Hi, everyone. Amber McCollum here. Good to see you all. Really excited to be with you for this training series. And as Cindy mentioned, do just monitor the chat. I'll be providing some links to all the information you need there along the way. So thank you so much for being with us, and we hope you enjoy the training series. So we'll go ahead and get started. Hello, everyone. Welcome to our first session in our training series, Introduction to Remote Sensing for Tribal Lands. My name is Amber McCollum, and I will be joined by my colleague and our project lead, Cindy Schmidt, throughout this series. For each week in this series, we will be focusing on a specific tribal region within the United States, and we will also be joined by representatives from those tribal regions to explain their land management needs. So we're really hoping to focus on the needs and issues and the uses of remote sensing on tribal lands. So let's first just provide a brief overview of what the course and what the training series will look like. This series will be provided via GoToWebinar each Tuesday and Thursday of October from October 6th to October 29th. All of the course materials can be found on the United Tribes Technical College course website, and the link to that is shown here. So also please refer to this website for guidance on how to obtain continuing education credits if you're interested in that. Also, that website is where you can find all the lectures, the course exercises, and the data that you'll need. And you should have downloaded the materials for the first exercise today if you'd like to follow along with our demonstration we will do at the end. If you have any additional questions at the end of each session, you can email myself or Cindy Schmidt, and our email addresses are shown there. As I mentioned, this training series will be a mix of lectures and hands-on exercises. All the exercises will be conducted in ArcGIS Pro and will be demonstrated in class. We have some materials for ArcGIS Desktop as well as QGIS, but they will not be the focus of the series, and we will not be providing demonstrations on those, but we have some documents on those for each of the topics as well. So here's a general overview of the training series. This week, we will focus on an introduction to remote sensing and how to view imagery Next week, we will focus on creating a land cover classification. In the following weeks, we will focus on change detection and time series mapping. Then we will have an overview of some useful web tools that can be used for remote sensing. So for today, we hope that you learn the types and characteristics of satellite imagery and know how to display, access, and analyze that imagery. It's also really important to understand the advantages and disadvantages of using satellite imagery. And finally, in our exercise today, we will go through how to display a Landsat image and analyze image bands. So for our first week, we are going to focus on the lands of the Navajo Nation. Here's a photograph of a water tank with the words "Water is life" inscribed on the side. For our first introduction, we will play a video that was created by Nikki Tully of the Navajo Nation, and she's also a graduate student at the University of Arizona. Nikki has been working with NASA, the Navajo Nation Department of Water Resources, and the Desert Research Institute on a project. And I'll leave it up to the video to describe that effort.
Dikodo trochido in ado indita trolachit ego eya na tlos adiki eya as dahat na tlos betro bilash la betro indita late na say betro as ego eya kundi ki eya Padafana Leda Tro Besto Padana Ahata Joita Deya Etronta Los in the Daleya Kundi Ki Eya Tronat Losiki Ki Eya Etlesh Behal Kadiki the Chita Ado in the Dae Quiki Eta Hotbeo Da Ketchi Eat Los Edo Dowd Eya Han so the Eya did not losh but or let wings go. Diki Eya a quig Han so go she Eya that then slen the ajit eaten zenko. A conde do yegon hastieno did Tronat losen arbitret na huntla. Kodan that the yosh. Sej da eia kode da trago da nas trandle. Ado in detta beshil wadiki, toil wadiki, beshna patliki da dat e. E kode eia e troha o ndal sa do hand so go she e troha ya atend a. E diki eia e ko trohaki johut ego sto. Archgosto hut ego eia ahil ego ebena hot ille.
Toeina, which can be translated into meaning water is life. The mentality of water is life is fundamental in sustaining the way of life for the Navajo Nation and for the Navajo people. The lifestyle of the Navajo people still heavily consists of agricultural practices, owning livestock, and hauling water. Due to frequent droughts, this lifestyle is impacted. The Navajo Nation is the largest Native American reservation in the United States. The reservation is approximately 27,000 square miles, an area that reaches into 3 states, which are New Mexico, Utah, and Arizona. Drought conditions influence the pattern of water availability found on the Navajo Nation, which can be linked to the domestic water supply, livestock, agriculture, and cultural and spiritual well-being. 2 members of NASA's Applied Science program, Dr. Cindy Schmidt and Dr. Amber McCollum, learned more about the drought issues being experienced on the Navajo Nation. While on a visit to the reservation, they took the opportunity to meet with the Navajo Nation Department of Water Resources personnel. As a result of this visit came the development of a 2-term internship project in 2015, which established the relationship and connection between NASA and the Navajo Nation. Dr. Schmidt and Dr. McCollum continue to help build other NASA relationships with the Navajo Nation. One such relationship resulted in the Develop Ames Navajo Nation Climate 1 and 2 teams. These teams created the Drought Severity Assessment Tool 2.0. Following the Develop project, NASA's Western Water Applications Office created the Drought Severity Evaluation Tool, otherwise known as DSET. DSET was co-developed with the Navajo Nation Department of Water Resources, NASA's Western Water Applications Office, and the Desert Research Institute, as a spin-off of Climate Engine to create on-the-fly maps, time series, and much more. The co-development partnership relationship resulted in a partner-driven, user-friendly tool. The DSET development relationship engagement continued with Carl McClellan of the Navajo Nation Department of Water Resources Water Management Branch and Dr. Amber McCollum of NASA's Western Water Applications Office, along with other personnel who took on the tool development to include the Navajo Nation rain gauge data, satellite data, model data sets, and drought and vegetation indices. Tide dona halkendaiki, wiki naskaiki, na behobekea bekake, do ande na etikitiki eya bekiskita. Tide kwiki, bena inishito kweke naskaiki, chahot eya bena noltra, nalido les. Tide naskahiki, dekit eya, di konde nanse, inde dale beketes tieki, deki eya saho, deki nalka, nalido les. Tide dona halkindaiki, halet ela, ado indeta, nanse, elto, halet ao eya nanstala, ado indeta, Tadiliehiki, elto, beketes tietoles. Do continal cloche pecatnal de do chios iniki wet ego bena inishiki da holta beketes tieto di de kono inishiki pechahot aniki eya yetes kanko yedo bitetot do indota nalka hiki edeki eya behos ani benache atotol nil na behope kea beka ke topa.
So that's just one example of the ways in which remote sensing can be useful for tribal regions, and it highlights a really great example of a project that we've been working on for a few years now. And later on in this training series, we will actually feature the DSET tool in one of our exercises, and that'll be in the last week of the training series. So do stay tuned for that. So before we get started with an overview of remote sensing, I wanted to briefly discuss NASA's applied sciences and capacity building programs. This animation shows the orbits of all the current Earth observing satellite missions. Note that our fleet of satellites that collect data around the same time, also called the A-train, are shown here in green flying over the screen. Many of these are joint missions with other countries or agencies, and they collect measurements of rainfall, clouds, sea surface height, ocean salinity, and so many other aspects of our Earth environment to really diagnose the health of our Earth system. Two satellites that we'll be talking a lot about during this series are Landsat and MODIS, so we'll talk more about those later. Within Earth Science at NASA, we have multiple programs. One of those is the Applied Sciences program, and this is where my colleague Cindy and I primarily work. And this is where NASA seeks to discover practical uses for NASA data that can help address management decisions in the areas of ecological forecasting, disasters, wildland fires, health and air quality, water resources, and capacity building. NASA funds projects like the DSET tool you just heard about, and also projects called MAPPed, where researchers at NASA and Stony Brook aim to study penguin colonies from space by mapping their guano, which they also call poo views. And this tool integrates remotely sensed inputs like Landsat, the satellite I mentioned, alongside sea ice data from MODIS. And this provides an assessment of Adelaide and other penguin species on this frozen continent. And recently they discovered the largest previously undiscovered colony of Adelaide penguins in the Antarctic Peninsula with over 1.5 million birds. Another tool that's created through applied sciences is called Snapshot Wisconsin. And here, remote sensing is integrated with citizen science and trail cameras to identify animals and compare point locations with ecological conditions from remote sensing. So the Wisconsin Department of Natural Resources uses this information to study animal population and dynamics. And within applied sciences is the capacity building program. And this really focuses on empowering communities to use earth science data. So this is really all about power to the people here. And within capacity building, we have three main programs as well as our Indigenous Peoples Initiative. SEVERE, or To Serve in Spanish, is a joint effort between NASA and USAID. This program is focused on international efforts where groups of scientists and decision makers work in country at hubs in places like Nepal and Kenya. And they have teams to create and manage ecological and climate risk for these regions. ARCET is an online and in-person training program where NASA scientists train professionals in air quality, disasters, land management, and water resources. So this is another really fantastic resource for all of you who are interested in continuing to use remote sensing for your work. The website is listed here, but there are trainings in a variety of topic areas, and everything is free and available online for you to watch the recordings and to download all the materials at any time. So it's a really great resource. Another program that you may be interested in is DEVELOP. And DEVELOP conducts 10-week projects with teams of interns that work to incorporate NASA data into decision making. So for all of the projects, the participants or the oftentimes student interns pair with a partner organization to help ensure that NASA data can be used for whatever decision that they're making. And this is a really fantastic program as well. And the internships are available almost year-round, with many of them in the summer. And then finally, our capacity building Indigenous Peoples Initiative. And here we seek to provide remote sensing training to the Indigenous community through a focus on place-based approaches and community engagement with links to Indigenous knowledge systems and earth science. So here are a few pictures from our past trainings, one where we partnered with the Samish Indian Nation and the Northwest Indian College up in Washington. And also we've worked with the Tribal GIS Conference and SIPI in Albuquerque, as well as working with the Bureau of Indian Affairs in Denver. So the three pillars of this initiative include community engagement, place-based approaches, and technical workshops. And so this all centers around the Indigenous knowledge system and the connections that we can make and the conversations that we can have to learn from one another. So this is really about engagement and capacity building, and it's our hope that through these relationships, we can continue to make progress in increasing the use of NASA data within these communities, and also bringing more Native voices to NASA, because we have a lot to learn from each other. One effort where we have worked to increase this engagement is with the Group on Earth Observations, or GEO, where we, through our partners, have created the GEO Indigenous Alliance. And this all began with a meeting last year held in Canberra, Australia, which was the first Indigenous focused session in the history of GEO at their GEO Ministerial Summit. And so this helped get the momentum going for our GEO Indigenous Alliance, and we're continuing this partnership. So as I mentioned, we also conduct technical workshops, and like those listed here, and much of the material for this training series was built off of these efforts and highlight some of these regions in the US that we've worked with. All right, so let's now jump into an overview of remote sensing. Remote sensing is the science of obtaining information about objects or areas from a distance, typically from aircraft or satellites, but it can also be from ground instruments like the image that you see on the left. The process of acquiring data from aircraft or satellites involves the detection and measurements of radiation at different wavelengths that are reflected or emitted from distant objects. For this training series, we're going to be focusing on satellite remote sensing, and it really depends on the application or the use of the data in terms of which kind of system you are interested in using. So you need to think about what kind of information do you want, and how much detail do you want that information, and how frequently do you need it. And we'll talk a little bit about this as we go through the presentation. So why is remote sensing useful? Remote sensing provides us with the ability to have consistent, objective and repeatable observations of a place. It's also most useful when compared with ground observations, but can be used for very large regions and remote areas where ground-based data collection may not be possible. Finally, having these consistent measurements over time allows us to examine changes on the Earth that may be occurring over many seasons or many years. And what can remote sensing be used for? The answer is many things, and you'll see some of that through this series. From conservation, like monitoring of a national park, which you can see in the green areas in the image on the bottom, to identifying illegal fishing through monitoring the lights on ships, like the image on the top, to monitoring wildfires, like you can see in the image on the top here, or tracking seasonal changes in vegetation with ground-based remote sensors, like the image on the bottom. So what is measured with remote sensing? When we think about optical remote sensing, this is how we think about it working. So we think about the sun, our energy source for the Earth. This electromagnetic radiation travels through space in the form of a wave. The energy from the sun hits the Earth, and the Earth absorbs or reflects that energy. The Earth also emits its own energy that can be captured by satellites. The energy that is absorbed, reflected, or emitted comes in the form of waves with different lengths in different parts of the electromagnetic spectrum. This picture shows different wavelengths of the spectrum, from long wavelengths on the left to shorter wavelengths on the right. Although we are talking about light, most of the electromagnetic spectrum cannot be detected by our eyes. The only part that we can see is within the visible part of the spectrum, and as you can see, that's a very small piece of the pie. Even satellite sensors only capture a small portion of this entire spectrum, and what we're really going to be focused on and interested here is from the visible to the infrared, and sometimes out into the microwave region. This is a simplified example of what happens when electromagnetic energy interacts with green vegetation. The figure on the left shows the incoming radiation in the visible spectrum, blue, green, and red, and the near infrared wavelengths. The blue and red energy is being absorbed, and the green and near infrared energy is being reflected. And this is why we see healthy vegetation as green, because the reflected green energy is what our eyes can view. And this is primarily due to the chlorophyll concentration in the leaves. Although we can only see the green energy, the near infrared energy really reflects very highly in vegetation. So we will take advantage of these features when we look at vegetation through our imagery. So every surface on Earth reflects and absorbs energy in a different manner. For optical imagery, the sensors are capturing similar data that we see with our eyes in the visible portion, and some that we cannot see in the infrared and microwave portion. So each object on the ground produces a unique signature of the amount of reflection or absorption of each wavelength. And we call this the spectral signature. And you can see in this image here on the bottom right, a typical spectral signatures for vegetation, where we see a little peak of reflectance in the green, but we see a really large peak of reflectance in the infrared. And so we'll be exploring these things in our exercises as well. So here is another figure of multiple spectral signatures from different types of objects on the ground. In green, again, you can see the typical vegetation signal with a little peak in the green and a high peak in the near infrared. You can see that water has low reflectance throughout much of the visible spectrum, and that soil has a steadily increasing reflectance across these different blue, green, red, near infrared ranges. So now that we have reviewed how objects interact with solar radiation, the next thing to understand is how satellites and sensors collect that information. Optical or passive remote sensing, which we'll talk about, really depends on the sun for its sole source of illumination. Solar radiation that comes from the sun passes through the atmosphere, hits a target, such as a forest or water or a house, and the energy is either absorbed or reflected. And as we previously discussed, different materials reflect and absorb differently at different wavelengths. Satellite sensors collect the reflected radiation in various wavelengths. So this different sensors collect this radiation in different ways. It's also important to understand that the satellite or platform carries the sensor or instrument. Oftentimes we use these terms interchangeably, so it can be a little confusing, but Earth observing satellites typically have names like those listed here. For example, the Aqua satellite has many instruments such as MODIS and SEERS and AIRS, and then the Landsat satellite has instruments like OLI and TIERS. So sometimes we use these interchangeably, but it's important to understand that for MODIS, for example, the MODIS is a sensor that's held on board the Aqua and Terra satellites. So there are two types of sensors, namely passive sensors and active sensor. A passive system needs an external energy source, and in most cases, this source is the sun. These sensors detect reflected and emitted energy from objects on the Earth. Using the example of green vegetation, passive sensors measure the relatively high green and near infrared energy that is reflected from the leaves. And then this reflected energy can also be converted into other biogeophysical quantities like temperature or soil moisture, just depending on the data that you're using and the application you are interested in. And some examples of passive satellite sensors are Landsat, MODIS, TRIM, which measures precipitation. And passive sensors and imagery will really be what we focus on through this training series. An active sensor, on the other hand, provides its own energy source. So an example is a radar sensor that sends sound waves and then records the reflection of those waves coming back from the surface. Since they don't need the sun, active sensors have some benefits that passive sensors do not. So they can be used during day and night. They don't need the sun for their energy. And they oftentimes can penetrate cloud cover, which is really helpful, especially in areas that experience cloud cover very commonly, like tropical regions. The challenge of active data is that it's oftentimes really difficult to process, and the data sets are really large, and many of them aren't global, so you don't have the type of coverage that you do for many of the passive sensors. So when thinking about these different sensors and satellite systems, they have multiple types of orbits. So each type of orbit has varying spatial coverage and temporal resolution, which we'll talk about what those mean soon. So we have polar orbiting satellites that essentially move around the Earth from pole to pole, and they have global coverage, but may not collect data over the same area as often. This really depends on the sensor itself. Non-polar orbiting satellites have generally move around the equator, and so they only collect imagery within a certain latitude range around the equator. And many of these are satellites that are used for monitoring things like weather patterns and precipitation. And then finally, we have geostationary satellites. And geostationary satellites just stay in the same exact place, and they monitor that same place always. The advantage of these is that they oftentimes can take multiple images and data per day, So you have really high temporal resolution, so you get the images really often, but they're fixed in one place, so you don't get oftentimes global coverage there. So now that we've discussed some of the aspects of satellites, let's talk about the types of resolutions. So we will discuss 4 types of resolution: spectral, spatial, temporal, and radiometric. So every data set that we analyze or use in remote sensing has variable resolution in each of these realms. So spectral resolution, as I mentioned, each satellite or sensor acquires data in different parts of the electromagnetic spectrum. Some sensors, like Landsat, are considered multispectral because they have a few bands or channels covering a large part of the spectrum. These bands are generally wide, meaning that a single band acquires data over a range of wavelengths. Some sensors are considered hyperspectral because they have a large number of bands covering many parts of the spectrum. So you can see here in this image, these images on the bottom, where we have Landsat, which is considered multispectral, which has bands that collect the electromagnetic radiation within a range and provide values for that entire range. And with hyperspectral data, that range is much smaller. So you're able to distinguish things like the difference between identifying just vegetation or the species or type of vegetation that you could do with hyperspectral. So each of these bands, each of these wavelength ranges can be displayed and manipulated as separate layers to generate the entire image. And we will discuss this in depth later on, as well as within the exercise. So for example, you have for Landsat, for example, you might have blue, green, red, near infrared, and mid infrared, and you'll have values within each of these wavelength ranges provided as separate layers. So we'll discuss this in more depth. Spatial resolution is the detail discernible in an image, and it's dependent on the sensor and refers to the smallest possible feature that can be detected on the ground. Most images are composed of a matrix of picture elements or pixels, which are the smallest unit of an image. Image pixels are normally square and represent a certain area on an image. And in this example here, in these images, you can see a comparison of different satellite images and what their spatial resolution looks like. From Landsat on the far left, which has a 30-meter pixel resolution, which means each value or square is 30 meters by 30 meters, all the way to, for example, QuickBird, which has a 1-meter spatial resolution. So you can see the level of detail is much more discernible on the ground from something like QuickBird, which is a commercial satellite. So to give you a little bit more perspective and try to put this in relative terms that you can understand, here's a pixel of Landsat 8 displayed over a baseball diamond. So a standard pixel of Landsat would cover the entire infield of a baseball field. If you had a 15-meter band, which is, there's one band on Landsat that's 15 meters, the panchromatic, that means you would get one value in the entire area between home plate and the dugout. If you were to have a 100-meter pixel, which is one of the thermal bands of Landsat, that would cover the entire baseball diamond and field. So you would get one value within these different squares. So the higher the spatial resolution, the less area is covered by a single image of a satellite. The examples shown here are MODIS, where the imagery ranges from about 250 meters to 1 kilometer in terms of the spatial resolution, but it covers a much larger area of much of the US and Canada in one image or swath. In comparison, we have the area over which Landsat collects an image, and Landsat has 30-meter spatial resolution, and you can see that the area, this is a picture of the San Francisco Bay, and it covers a much smaller region. So there are trade-offs here between spatial resolution and extent. The temporal resolution is the time it takes for a satellite to complete one orbit cycle, or, for example, revisit the same place on Earth. The temporal resolution depends on many things, including the swath overlap, so the area that they image, that the satellite takes an image, like I showed in the last slide, as well as the orbit and many features of the satellite itself. So when we think about temporal resolution, it's really about the revisit time. How often is this satellite going to take measurements of the same place on Earth? With Landsat, that revisit time is about every 16 days. With MODIS, it's about daily, and it really just depends on the satellite or sensor that you're using. The radiometric resolution refers to how sensitive the sensor is to recording the electromagnetic energy. So this really is about how the sensor can discriminate between very slight differences in energy or reflectance coming from the ground. The finer the radiometric resolution, the higher of the ability for it to detect these small changes. And this is generally represented in an image by brightness levels. And brightness levels can range from black to white and all of the gray levels in between. Different bits are often are associated with varying levels of this radiometric resolution. And so if you have a lower bit sensor, you're going to have less ability to discern between different gray levels within your image. And I'll show an example of what that looks like now, because it's a little obtuse to think about what this really means. So here's an example of differences, how differences in radiometric resolution look and how you get different gray levels. So if you just have 2 levels, all you would see is black and white. But if you had 16 levels, you can start to see that maybe this looks like a road and maybe some buildings through these different gray levels. So that's an important feature. As we mentioned previously, each pixel provides one measurement of the reflected imagery on the ground. The values will display the brightness or reflectance of the object on the ground for each band or wavelength range. So imagine that what you see here is one band of a Landsat image. And this is an example of Landsat 5. And notice that these reflectance values may be associated with different features that we observe on ground. And the numbers go from 0, indicating no reflectance, from 255, indicating the highest form of reflectance. And you can identify and match up the colors in the squares with the reflectance values on the right. So you can see a reflectance value of 0 is indicated by a black square, and somewhere in between 0 and 155, 170, for example, would be some sort of gray level. So when you're thinking of using remote sensing for answering some question in your region, there are many considerations. So first off, what's the geographical, phenological, and atmospheric condition So for example, are you interested in studying a region that is constantly covered by clouds? If so, you might not want to use optical imagery because it'll be difficult to penetrate those clouds. Those clouds will be in the way. What are the spectral regions? Are you interested in discerning different land cover types or different types of vegetation? And depending on what you want to view on the ground, that might change what kind of sensors you use. What's the spatial resolution? How large of an area are you interested in studying? And can the satellite sensor that you are using provide you with enough detail to make decisions or identify things on the ground at the level of detail that you need? How often can you obtain imagery? That's really important. If you're thinking about studying floods and you only get an image every 16 days, that might not be frequent enough to study the dynamics of that change. How long do you have the data for? These satellites are often designed to only last a few years. They many times last much longer than they're designed to, but how long is that record and how far back do you need to go? Are there costs involved? Are you thinking of commercial satellites where you have to pay for the data? And what are the future possibilities for obtaining these kinds of data? So again, there are many advantages and disadvantages to remote sensing. Some advantages, as we've mentioned, they have the ability to provide oftentimes global coverage, consistent measurements, ability to analyze regions where ground measurements are really difficult to obtain. However, there are disadvantages. Sometimes they don't provide the level of detail that you need. The optical imagery cannot detect below the canopy cover of a forest. So if you're interested in understanding what's going on in the understory, you wouldn't be able to analyze that through optical remote sensing data. Many of the sensors can't penetrate through water, and there is a cost associated with some. All NASA data are freely available, and then there's also the technical expertise that you need in order to analyze these data. Okay, so moving on to displaying imagery, which will be the focus of our exercise today. As we mentioned, data are provided as separate layers for each of the identified wavelength ranges. So if you displayed one band, it would look like various gray levels, like we reviewed in the radiometric resolution slides. In order to display color, you need to combine the different bands like red, green, and blue. And this goes back to the color model. Think back in art class in elementary school where you mixed your colors together to get new colors. And the same idea can be applied to remote sensing images. So we can analyze these different layers, say, of a Landsat image, and by identifying these bands. And so this is just some of the terminology that we're using. Here we have blue, green, red, and then the near-infrared and mid-infrared bands. When we use a GIS, such as an ArcGIS, we will input each of these bands or layers into a color channel to highlight different features on an image. So for example, when we look at ArcGIS, we can put certain image bands into the red, green, and blue. And so you'll get a chance to try this out in the exercise. So here you can see what the bands and color channels would look like when we put a band within a particular color channel. So let's start with true color. If we were to put the red bands into the red channel, the green band into the green channel, and the blue band into the blue channel, this would provide a true color representation of an area in the way in which our eyes would view the landscape. If we were to switch this up a bit and for example, put the near infrared band into the red color channel. Remember, when we're looking at vegetation, vegetation reflects very highly in the near infrared. So if we were to put those high reflectance values of the near infrared into the red channel, our vegetation would be displayed as bright red in the image. Then we can put the red band in the green channel and the green band in the blue channel to really identify and highlight these vegetated areas. And in the remote sensing world, we call this false color. Another option that we'll play with in our exercise as well is the use of the mid-infrared band. So the use of the mid-infrared and the near-infrared bands. So for example, if we put the mid-infrared in the red channel, and then we move that band of really high reflectance into the green channel, the near-infrared into the green, our vegetation will really pop and will really be highlighted as bright green. So that really displays the differences between the slight peak in reflectance in the green and this really large peak of reflectance in the near infrared when we look at vegetation. So by essentially by putting these different bands into these different color channels, we can modify the way images are displayed to highlight specific features on the ground. So for example, in this example, if we were to take the band 3 or the green band and put it into the blue channel, the red band into the green channel, and again, the near infrared band into the red channel, we would get the false color image. And we will play with these different ways in how we can display imagery through the exercise as well. So when we also think about these different channels, think back to our color mixing model and the values of reflectance that we would see within each of these bands. So if we understand the lowest reflectance to be 0 and the highest reflectance to be 255, imagine a scenario like this, where we have zeros in terms of the reflectance in the blue, green, and red channels. So for this example, what do you think the image would look like? And you can use the chat function to type in what you think, what color would be displayed in the image here if we have 0 values in the green, blue, green, and red. And I'll give you all just one moment. So hopefully many of you got this right. We would see this image as black because we are getting 0 reflectance. All of the energy is being absorbed. So we would see this whole image as black. What if alternatively we had the highest reflectance values in all 3 of the channels? And I'll give you all a moment to type in your answer there. So 255 is the highest reflectance that you can see. All right, so hopefully many of you said it was white. So if all of the energy is being reflected, the image will appear white in all of these channels. Okay, so how about this one? We're getting about middle level reflectance in all 3 of the channels. Yeah, this one will be gray because it's somewhere in between the black and the white. Okay, so how about this example? We have high reflectance in the blue with 255, low in the green and red. What would this look like? Yeah, this would look blue, right? Because we're getting all the reflectance in the blue channel. How about this one? You got it. This one would look green because we're getting all of that reflectance in the green channel. Okay, and for this last one, maybe a little more difficult, think about those mixing colors in kindergarten art class. So what would this one look like? Okay, this one would be yellow because when you mix green and red, you get yellow. And for all of these pixels, we have the same amount of reflectance in both the green and the red. And so we get this sort of pure yellow color coming through. So more on that as we go through the exercise. So finally, I just wanted to mention a few things about the imagery you'll be looking at today. And we will be using Landsat imagery. And Landsat began, and the legacy of Landsat really started in the early 1970s, and have gone through multiple different satellites all through present day. So most recently, Landsat 8 was launched in February of 2014. So the beauty of this is that we have continuous, fairly high resolution data over many, many years. And this slide provides some of the information about those different bands and the spectral characteristics of Landsat. The graphic here at the bottom shows you that these data are collected in different bands, blue, green, red, near infrared, mid infrared, and then it shows you the wavelength ranges here. So you can then compare different types of Landsats across multiple years. So all of the bands along the top here are from Landsat 8, and then we have the sort of other Landsats 4, 5, and 7 with their ranges here. So you can see they are very similar, but there are some differences. And so it's really important to understand what the differences in band numbers and spectral ranges are when you're examining multiple different types of Landsat images from different Landsat sensors. So this table just provides an overview of each band. So it gives the specifics of the wavelength range for all the Landsat 5 and 7 bands and the Landsat 8 bands. So you can see there are some similarities, but there are some differences. So you just need to keep those in mind as you work through looking at the exercises and analyzing imagery from different Landsat satellites. All right. So that concludes the very long lecture, I know, for this first session. And now we will jump directly into our first exercise, investigating a satellite image. And just bear with us for a few moments as we transfer over to my colleague, Cindy Schmidt, who will be guiding you all through the exercise.
Perfect. Thank you, Amber. Yeah, as Amber mentioned, while I'm switching over here, Amber mentioned that this first lecture is always the longest because we have a lot of information to tell you, and at the same time, the first exercise is usually the shortest. So in the following weeks, days and weeks, we will have, it'll probably be a little bit more balanced. Well, we'll have a little bit of lecture and a lot more exercise, because really our philosophy is sort of learned by doing. We need to do the lectures, of course, to provide you background information to the exercises, but really, especially for any kind of, whether it's GIS or remote sensing or whatever, learning by doing is really the best way to figure out how this stuff works. So hopefully you can all see my screen now. And we're going to start, as Amber mentioned at the very beginning, we're going to be using ArcGIS Pro. And so that's the screen that you're seeing right now. We are using Pro primarily because we know that the Bureau of Indian Affairs Geospatial Group has an agreement with Esri to provide Pro to all the tribes. And so hopefully you all have access to Pro. If you don't, what you'll probably need to do is just follow along with these exercises. And as Amber mentioned previously, we also have written up the exercises in ArcGIS Desktop, so the previous version of ArcGIS, and we've also written them up in QGIS, which is an open source software package for doing image processing and other kinds of GIS analyses. So if for some reason you don't have Pro, you can use the other exercises. We just won't be demonstrating them in this webinar series. So hopefully all of you have access to the exercise that the document that we have, so you can follow along. You can actually follow along and do the exercise at the same time, or you can just watch, follow along, and then actually do the exercise at a later time. The data that you should have is listed on the first page of the exercise. So you should have a folder that has some Landsat 8 data in it. It's a big folder. It's a big file. So those files are quite big. So just a heads up on that. So hopefully you've downloaded that successfully. You should also have an Excel spreadsheet file that we've also given you. We'll be using that toward the end of this particular exercise. So I'm on page 2 now of the exercise. So we're going to be actually working with a Landsat 8 image that covers portion of the Navajo Nation. And I'll describe a little bit more as soon as we bring up the imagery. The other thing I do want to note here is that although we will be using Landsat imagery throughout all of these exercises, all of the methods that you're using to display and imagery can be used for other types of imagery as well. So you can use the same methods for looking at high spatial resolution imagery, like the digital globe imagery, and drone imagery. If you happen to have that, you can use the same methodology for viewing and analyzing that imagery as well. So I did want to let you know that although we are using satellite imagery, you can replace it with other imagery when you start using this yourself. Let's see. So let's go ahead and get started. When you open up ArcGIS Pro, the screen that you see right now is the screen that you'll see yourself. And what we're going to do is start a new project. So in order to do that, you see new is selected here, and I'm going to click on blank template, the map. And what will come up is a dialog box that says create a new project. So that's what we're going to do. So we're going to call this project, the default right now is usually my project or my project 1. I've done this several times, so this is my project 2. And we're going to call it, we'll call this one NASA _ exercise 1. Okay. And then make sure that you navigate to where your data are. So I'm going to click on the folder on the right and navigate to where I know the data are. I've called that folder exercise, well, EX1, or you could call it exercise 1, whatever you want to do. So I'm going to click on that folder because that's where I want it to go. And then you want to uncheck create a new folder for this project. And then say okay. So the great thing about doing it this way is that the default location will always be this folder for your data. All right, so in a minute, everything's going to pop up here. And in Pro, the default, when you open up a map, is a couple base maps here. We have a world topograph, as you can see, and it's centered on the U.S., and then a hillshade map as well. And I really like this feature because when you open up imagery, it'll open it up in the area that you've specified, and you can always have that as sort of reference data, because sometimes when you have imagery up, it's kind of hard to tell where you are. So I really actually will like this feature. So the first thing we want to do is open up our Landsat image. And to do that, you'll want to, there's several ways you can do it. You can do it with this catalog pane, which sometimes will open up automatically, but as you can see on my screen, it didn't open up automatically. So the best way to do that, if you want to, we'll do it several different ways. We'll start off with the catalog pane, but if you go to the very top where it says View, and then you click on Catalog pane, it will come up on the right-hand side, hopefully. And then you'll see a list of different things that you have access to. So if you click on Folders, you'll see your exercise 1 project show up there, your folder. And then if you click on that, you'll see all the information, all the files that are within that exercise 1 folder. And the Landsat image will be in this file that has a very long name that starts off LC08, which is Landsat 8. So we'll open up that folder. So click on the triangle to the left of that. Takes a little bit, and you'll see a whole lot of files in there. So I'm going to scroll over so you can see, because what we need to know is, I'm going to make this a little bit bigger so you can actually see the bands. One of the things that we do in this particular exercise and the first couple of pages is explain what goes into a Landsat name. It's quite extensive, as you can see, but the couple of things that you need to really focus on, or that you care about, first of all, this LC08 means it is Landsat 8. Where it says 035035, that's called the path and row. So the path and row is essentially a grid system for Landsat imagery throughout the whole world. And so what this says is that this particular image is path 35, row 35. And then the other thing you need to know is the date of the imagery, which is specified here. 2016, 09/16, so September 16th. And then the last thing that's most important actually for this particular exercise is the B1, B2, B3, B4, etc. on the end. So that tells you which band that we're looking at. So when you download Landsat imagery, it all comes in individual bands. And what we're going to do a little bit later on is actually combine several bands into one file. It just makes it a lot easier to work with the imagery when it's all in one file as opposed to individual bands. So the first thing we're going to do is actually just look at a single band. So if you go down to band 6, and the other thing I do want to note is it looks like the Landsat bands are in this file twice, but The prefix for these first several files has the dot and an underscore, so don't use those files because those do not display the imagery. It's not actually the imagery. What we want are these files below that don't have the dot and the underscore. So we're going to go down to where it says underscore B6. If you right click on it, it says add to current map. So that's what we're going to do. And so it will show up in a minute on the left hand side. Sorry, I just didn't go to full screen anymore. There we go. So sometimes it takes a little while. My ArcGIS Pro may be a little bit slower than yours, and that's primarily because my ArcGIS Pro I have to access through the server that's at my work. And so I have to use a VPN connection to get to it. And my internet is not great here at my house. So VPN slows things down. So mine may be a little bit slower than yours, just to give you a heads up on that. So now you see band 6 appearing in your window, and the contents on the left. And you notice that it is black and white. There's no color here because, as Amber explained, in order to see color, you actually have to display 3 bands at once. If you only display 1 band at once, then you're going to see that image just in gray levels in these in this black and white color. So I'm going to go ahead and close the catalog pane because we don't really need that anymore, and you'll be able to see the imagery a little bit better. At this point, if you want, you can turn off the topographic map, shade map. I'm going to keep it on because I think probably there's a lot of you that aren't familiar with this region, and sort of click on and off the images as we go through. You can kind of orient yourself in terms of where you are. And again, I'm going to leave the image off just to show you. This is part of the Navajo Nation, which covers parts of 4 different states. And in particular, there's some really interesting features in the Navajo Nation. On the left here, you see Canyon de Chelly, which is a very sacred area for the Navajo, and it's stunningly beautiful on top of that. And then we have the Chaco Culture National Historical Park, which is also very sacred to the Navajo. It's also a really, really very interesting place to visit. And then the 2 other kind of main features that we'll be talking about throughout this particular exercise are the Chusca Mountains. So you see that mountain range kind of going diagonally between Arizona and New Mexico right here. And also Farmington, this little town up here, because there's some agricultural areas that we'll be using a little bit later on as well. So that's just to orient you to where we are. I'm going to turn back on the imagery, and you can kind of see some of those features that we're looking at now, but we'll be able to see it more in color in a minute. So the first thing we want to do to look at the imagery in color is, again, we need to combine all of those bands together into one file. And so that is called a composite. In order to create a composite of all the bands into one file, we need to open up the Geoprocessing Tools box. So at the very top, under the Analysis tab, you'll see this Tools in red. So click on that. And then to find the command that we want to use, type in composite. So I already have it written in here. And then if you do a cursor return, if you type it and do a cursor return, then the first option that will show up is composite bands. So click on that. And then we're going to choose our bands by clicking on the folder on the right. And again, don't pick the files that have the dot and the underscore. we're going to only choose the files that are kind of in the bottom half of this list. And what we want to do is select bands 1 through 6. So I can just click on 1 and then shift click to down, or sorry, 1 through 7. And then shift click and include bands 1, 2, 3, 4, 5, 6, 7. And click OK. And you see them show up under input rasters. Then for the output raster, let's go ahead and navigate. If you click on the file on the right, navigate back to your exercise 1. And then we're going to call this Landsat _ exercise 1.tif. Make sure you put the TIFF extension on it, because the default, if you don't, is an ArcGrid file, which is fine. You can still work with the ArcGrid file, but the TIFF just allows you to have to use this particular file on other applications if you want. It's a little more flexible than the grid file. Okay, so we'll save that, and then we'll click Run at the very bottom. So it takes a little while because these images are quite big. And plus, as I said before, I'm running on VPN, so everything runs a little bit slower for me anyways. And as soon as this finishes, then you're going to see the multi-band image appear in the contents window on the left-hand side. So we'll wait a little bit. Hopefully you guys are all able to run that. If you have any questions while you're running it, please feel free to put questions in the chat window. And also, please, this is recorded, so we can't, it's hard for us to sort of slow down or speed up in real time. But both Amber and I are available to answer any questions that you might have as you're running through this. So it's almost finished. See, it's doing its little thing on the bottom. It's running. And then we'll be able to look at this image in color. The one thing I want you to note on the left-hand side, you know, if you look at your Landsat, your band 6, and you'll see the values range from 0 to 42,000. That's because Landsat 8 images are 16 bits. So Amber, when she was giving the examples before of 0 to 255, those are 8-bit images. So Landsat 5 and 7 are 8-bit images, meaning they have 255 gray levels. But Landsat 8 are 16-bit images, which means they have over 65,000 different gray levels. So it has a little bit, it's not a higher spatial resolution, but you can distinguish between different features a little bit better because it has more bits. So in this case, if you look on the left at your band 6 again, the minimum value is 0, which is most often the background data, and then your highest value is 42,521, and that's because it's 16-bit. All right, so my image has now appeared. It's finished doing the composite, and as you can see, the colors are really kind of strange. And that's because we need to change the band combination. So we kind of need to go through that that exercise of putting different bands in different sort of color guns. But before we do that, in ArcGIS Pro and actually many different geospatial software packages, you have to run what's called calculate statistics on the images, because it basically allows the software to recognize the different values within each of the bands. So we're going to use the geoprocessing tools again to do that. I left mine up, so I'm just going to go back to where we have the search tool. I'm going to clear composite, and I'm going to type in calculate statistics, and there it is. It popped right up under data management tools. So I'm going to click on calculate statistics, and my input raster data set will be our newly formed Landsat composite. And unfortunately, you have to navigate to it. It should just pop up, but okay. And we put it under our exercise 1 folder. So it should say Landsat x1.tif or whatever you decided to name it. So select that. And then leave the X skip factor and the Y skip factor as 1. And we're going to go ahead here and say ignore value 0 because as I explained before, the 0 value is typically the background data. There's very rarely ever any pixels with 0 value in the image. So we're going to ignore that value and everything else will leave the same. And then we'll just say run at the bottom. So we'll let it calculate the statistics, and then we'll take a look at how you can look at information about this image in a minute as soon as it finishes running. This is a really useful process to run because it also allows you to actually look at the imagery with better colors. Again, the software takes a look at the statistics to do these stretches on the imagery so you can look at it. So it's important that you actually run this process on any imagery that you bring into ArcGIS Pro. The other thing I wanted to mention, a lot of people ask, why is the image look tilted? So why isn't it, perfectly square? And that's because the image is facing north and the path of the satellite is actually tilted like that. So what you're seeing is part of the path of the satellite that doesn't run exactly north to south. It's a little bit tilted from the northeast to the southwest. And so those areas of black along the edge are actually, there's no data in there. That's just background data. If you're to clip out an area within this image, it would be square. It wouldn't look tilted like this, but this is just when you download a whole Landsat image, they typically look tilted. So if you download another image and it looks tilted, then you're doing the right thing. Okay, so now our calculate statistics has finished running. I'm going to go ahead and close the geoprocessing box just to make it easier to see the image. So let's just explore the statistics a little bit and the properties of this particular image before we change the colors. So if you go back to the contents window on the left-hand side and you right-click on the name of the image, you'll see lots of different things come up. We'll be using this a lot, so hopefully you'll get some good practice doing this. And you're going to click on properties, not symbology yet, properties. So there's a lot of different information about this image. You can click on metadata. There isn't a lot of metadata right now, but you can certainly put metadata in there. So if you click on source, you can get raster, and you click on the raster information underneath the data source, you'll get specific information about this imagery. So how many columns and rows, so essentially that's how many pixels there are across and down, about 7,500 to 7,700 columns and rows. how many bands we have in this particular image. So we have 7. And then the cell size is 30 meters by 30 meters. And then there's a little information as you scroll down. As you see, the pixels, it's 16-bit, as I told you before. So the maximum gray level value will be around 65,000. And then if you keep scrolling down, it gives you a little bit more information. And then if you go to statistics, you'll see some information for each of the bands, the minimum value. And again, this is really because the background minimum is 0 is because the background is 0. It's including that in the statistics. And then the mean value, so that's the mean pixel value for the whole band, and then standard deviation and so forth. And then, of course, the maximum value. So this just gives you some basic information about the imagery if you're curious. Okay, I'm going to go ahead and close that, and let's go ahead and change the band combination so the image looks a little better. So there's a variety of ways you can do this. The first way we're going to do it is by selecting symbology. So again, if you right-click on the image on the left and you select symbology, you'll see the symbology window show up on the right-hand side. So there's lots of things in here. The first thing under primary symbology is you'll see RGB. Just leave that the way it is. With imagery, raw imagery anyway, we want to keep it RGB. Now, the next part is where we can change what bands go into what color gun. So this is similar to what Amber was showing you before with the true color and the false color and that sort of thing. So the first thing we're going to do is what we call true color. So it's kind of like the way you would see it with your eyes. So what we want to do is put band 4, which is the red band in the red, what I call color gun. You're going to see it change real time as we go. And then for the green, we want to put band 3, which is the green band. And then for band 2, we're going to, for the blue band, we're going to put band 2. And we'll just leave it like that. And so let's just, actually, let's close the symbology box right now, because we're going to, the next band combination, we're going to use a different way. So we're going to close that. So let's take a look at the image. So if you were flying in an airplane overhead of this area, this is kind of what you would see. The vegetation is greenish, depending on how much water it's getting. So you can see in the little circles where you see little circles, you can see some greens and some dark greens. And then in the Cheska Mountains that I mentioned before, it's kind of a dark green. And so we call this, and then everything else is kind of just bare ground. There's a whole lot of vegetation. It's a very dry area, dry environment, and the rest of the areas. And the reddish areas are just indicative of the type of soil, the different kind of soil types that you see in the region. So we call this true color because it's kind of like how you would see it with your eyes. So next we're going to bring up false color, where the vegetation will be red. And then another way of changing the band combination is to go to the contents window on the left-hand side. And then if you right-click on where it says red band 4, you'll see the different options of the bands available to you. And this is actually kind of a faster way of doing it. So in this case, we're going to want to put band 5, which is the near infrared band, in red. We're going to put band 4, which is the red band, into the green. And we're going to put band 3 into the blue band. So now you can see the vegetation really pops out here because it's a lot easier for our eyes to distinguish reds than greens in some cases, depending on the shade of the green, especially in contrast to the background area. So again, you can see the Cheska Mountains here that run diagonally across between Arizona and New Mexico, right here as a sort of a darker red color. And then up here in the top of the image where you see the little red circles, that's all agriculture. So it's center pivot agriculture, and it's highly irrigated, of course, because it is agriculture. So that makes it a very bright red. The other thing kind of interesting here is you can see this is actually a river going along the top of the image again, and this is vegetation located along the river, which is also red. So this is, a lot of people really prefer to look at satellite imagery, or actually any imagery, this way, but you can only do this if you have the near infrared band in the red color gun. Okay, so for the last band combination, we're going to bring in the shortwave infrared or the mid-infrared band because that allows you to see some even different characteristics of the image. So we'll go through the same methodology that we just did with the false color, where we'll right-click on the red band 5, but instead of band 5, we'll put band 6. Then we'll change the green band to band 5. And now you can see the vegetation as a much brighter green than we did with the false color. With the true color imagery when we were doing it like we would see it with our eyes. And that's because we're putting the near infrared band, which as you remember that Amber told you, has really high reflectance for vegetation. And so they're very high values for vegetation in that near infrared band. And then we're also bringing in the mid-infrared band, which is really sensitive to moisture content of both vegetation and soil. And so a lot of the differences that you're seeing, especially in the non-vegetated areas, are due to moisture differences. So generally, if they're darker, that tends to indicate higher soil moisture. And for vegetation, if it's brighter, so for example, these, I'm going to zoom in a little bit here, to these agricultural areas, they're quite bright, which means they're getting a lot of water. And same with the areas along the river on the top. If you move down to the Cheska Mountain regions, it's still quite green, but it's darker because of the vegetation types and because they aren't necessarily irrigated. And I guess this brings up also one thing that I wanted to show you probably earlier is how to zoom in and zoom out. The interesting thing about ArcGIS Pro now is that you can just point to an area and then use your cursor to scroll in and out. So I have a little wheel on my mouse, and I just use that little wheel to zoom in and out of a particular area. And then if you move your cursor to a different area, it will zoom in to that. And then to pan, all you have to do is sort of left click and hold and then pan. You can pan that way. So you can practice a little bit with how to move around in your image. And then if you want to zoom all the way back out to your full image, the easiest way to do this is to right click on your imagery and then go to zoom to layer. and then it zooms all the way out. We're going to be using these features quite a bit throughout our webinar series, so you'll get some good practice. So one of the main questions that I really like people to truly understand is when you're looking at imagery, you know, why is it that you can see vegetation as red in some images and green in some other images, which we explained here, but it's really important for you to understand how that works, because when you display any imagery, whether it's Landsat or drones or high spatial resolution imagery, you'll have the same options to look at imagery in different ways. And so if you really understand which band combinations that you prefer, and whether you prefer to look at vegetation as green or red, you know, it's really important for you to understand why we're seeing these different sort of band combinations. So in order to do that, we're going to start looking at different spectral characteristics of the imagery. And we're going to do this sort of in a what I call sort of a quick and dirty way. But in order to do this, we actually need that Excel spreadsheet that we gave you earlier. So what I'm going to do is put this window smaller so I can actually bring up the Excel imagery at the same time so you can see both. So I'll make this window a little bit bigger, and then I have my spreadsheet also. Make that a little smaller. There we go. So hopefully you all have downloaded this spreadsheet for you to look at, because this will help you get through this last part of the exercise. So let me explain a little bit what you're seeing here in the spreadsheet. So we have these different in this B column right here, we have these different features that you'll be able to see in the imagery. We have agricultural vegetation, we have forest vegetation, we also have urban, of which there isn't a lot in this image, but there is some. We have bare ground, so that's basically, you know, parts of the area that don't have very little to none vegetation on it. And then we have water. Again, there isn't a lot of water in here, but there is some. So we're going to get the pixel values in 3 different bands for each of these features. And the bands we're going to be looking at are, for this Landsat image, are band 3, which is the green band, band 5, which is the near infrared band, and band 6, which is the mid infrared or shortwave infrared band. Okay, and then what we're going to do is create spectral signatures for each of these different land cover types. And so the way to think about spectral signatures is kind of like a fingerprint. Each one of these different land cover types has its own unique spectral signature. And also, the data that I collect for mine may be slightly different than what you get for yours. So every type of vegetation type or land cover type within these areas will be different as well. So just your results may not exactly be the same as mine, and that's okay. So we want to make sure that we have displaying right now band 6, band 5, and band 3. So the first thing we're going to do is get some pixel values for the agricultural area. So that's this area that's kind of just south of Farmington. Farmington is a little town located right here. And the center pivot agriculture, we're going to zoom into that. Okay, just far enough so you can sort of see, we don't have to zoom too far in, but you're going to want to try to get one of these really bright green areas and a pixel within those bright green areas. You can zoom all the way in to actually make sure that you get an individual pixel, but you don't necessarily need to do that. So in order to get pixel values, we're going to go up to the top of the window here and select map. And under map, you'll see the explore icon right here. And mine's already selected. But if yours isn't highlighted blue like that, just click on it. And then if you click in one of these bright green areas, I'm just going to pick this one right here. What will pop up is a window that gives you the pixel values in each of these 3 bands that we're displaying. So that's this window that showed up right here. And we're going to take these numbers and type them in to your table, your Excel table. Okay. And the one thing to just remember is that the order that these numbers show up in ArcGIS Pro is red, green, blue. So you're going to type them in to the spreadsheet kind of backwards, right? So we'll start with the red. And in my case, I have 1, 2, 0, 4, 6. Green, which is 2, 3, 5, 9, 4. And blue, which is 8, 2, 9, 4. 8, 2, 9, 4. Okay. And that's all we need to do. So go ahead and close that pop-up window. Let's zoom out to the full image again. So again, if you right click on the Landsat image and go to zoom to layer, we'll zoom back out. And the next area that we want to get pixel values for is the forested area. So we'll choose the Cheska Mountains here. So just zoom in anywhere in there. Use your mouse and you can just zoom way in. Now, if you look, the more you zoom in, the more sort of variable green colors that you see. We're gonna, a lot of this is due to the types of vegetation that you see, but it's also due to shadows due to the angle of the mountains. And so oftentimes the dark sides are the north-facing slopes, for example. But we're going to go ahead and choose a pretty dark area for our pixel values. So again, just make sure Explore is clicked on, and then I'll click on a dark area. It could be any of these dark areas. And you'll see those pixel values pop up again. So we'll type that into our Excel file again. In my case, red is 7448. Green is 10835. And blue is 7076. Okay, let's go to urban next. So I'm going to close my pop-up. I'm going to right click on the image, go to zoom to layer. Now there's a couple urban areas here. There's one up near Farmington, which is in the top, and then there's, I think it's Gallup down here, kind of just a little bit north of where you see these white clouds here. So I'm just going to go into Farmington. So I'm going to zoom in up here, and you can see this little community. So of course, the more you zoom in, the more pixelated it gets. And as you can see in urban areas, it's quite variable. So we have a lot of green, which means there's a lot of trees in this particular urban area. And then you see some kind of purple colors. So that just depends on the surface. It typically is asphalt, which is black. Right? So the road here that you see is asphalt, and then you see very bright white colors, which is usually the tops of buildings, depending on what that material is. So we're going to choose one of the white buildings. I'm going to zoom way in here, and I'm just going to go ahead and click inside the this white building right here, and then we'll get those pixel values popping up. And you can see those values are quite high across the red, green, and blues, but we'll type those in. Red is 26036. Green is 319 149. Is band 3, or the blue band, is 26618. 26618. Okay, 2 more to go. So we'll go ahead and close this again. Let's zoom out. Where's my mouse? Sorry, my mouse pad almost fell off. We're going to zoom out, zoom to layer again, zoom all the way back out. And there's a couple water bodies here that we can focus on. Actually, next is bare ground. So there's a lot of bare ground here. So let's zoom into one of these sort of pink areas that we see in the middle of the image. I'm just gonna zoom in here. And really you can kind of pick anything, anything that you see here. I'm just gonna choose something up in this area. Click on that. Put those values in here. Red is 22381. Green is 18177. And blue is 13206. Okay. Last one. Let's do water. Close the pop-up. Zoom back out. So there's a water body up here near Farmington, and there's also a very small one here in the near the Cheska Mountains. So I'm just going to zoom into that one near the Cheska. It's quite blue, actually. And I'll go ahead and click in there. And I will put those values in. So red is 5136. Green is 5722. And blue is 10176. Okay. So we're done with that. So let's take a look at this Excel file a little bit. I'm going to just put this over the screen, make it a little bit, there we go. Maybe zoom in a little bit so you guys can all see this. Hopefully you have a graph that looks like mine, or somewhat like mine. It may not be exactly the same. And what we want to do is take a look at this. So as you can see, each of these land cover types have different spectral signatures. That's what we just created in this graph on the right? So urban built, that very white area, very bright in all 3 bands, is quite high. Kind of peaks in that in the near infrared band, but it's all generally quite high compared to the other 3 land cover types. Now, if we look at the 2 vegetation types, we have the ag vegetation, which is the light green one here, and then we have the darker vegetation right here. So notice they have very distinct characteristics where they have a peak in the near infrared band, and that's because vegetation reflects very highly in that near infrared band. And with irrigated vegetation, such as the agriculture, you're going to have a much higher values than in sort of the forested areas. So that's why those values are so much higher. Bare ground is also quite high, so it increases through the shortwave infrared. And then water, which is interesting, in the blue band, or actually I think that's the green band, but the lower band wavelengths, you're going to see higher values for water. And if you think about it, when you look at water with your eyes, it looks blue or green, and that's because it's reflecting those wavelengths. And so you're seeing that here in this chart, and that particular body of water was quite blue, actually. So the values compared to the other wavelengths, near infrared and shortwave infrared, are going to be much higher. So this gives you a lot of information about the features in that image, in the image. This is kind of really really how we're going to finish this particular exercise, but I also want you to notice that, you know, going back to that question about why do you see vegetation as green or red in an image? So the near infrared band, where it says here wavelength 860, and in the case of Landsat 8, the near infrared band is band 5. Wherever you put that near infrared band, whether it's in the red color gun, I call them color guns, but red color band that ArcGIS Pro has, or the green one, that's what color your vegetation will be. So if you put band 5 into the green color gun, your vegetation will be green. If you put it into the red color gun, your vegetation will be red. Okay, so if you guys get that, you get like that's 50% or more actually of what remote sensing is about. So at this point, I am going to end this particular exercise. We will open up the floor to any questions that you might have. Amber and I will be able to answer them either in the chat or live. If you have some questions, specific questions about this exercise. If not, please, if you're working on this in the next couple days, please feel free to email us with any questions. And then we'll start with a new lecture and exercise on Tuesday. So thanks so much for joining us. And we look forward to talking with you again on Thursday.
All right, everyone. So that concludes our first course for the week. We do have some questions that came up in the question box that Amber's bringing up our Google Doc where we're keeping track of the questions that come up so you can all see them. And just to let you know, we will also make this Q&A document available for all of you later because sometimes we put resources in there that might be of use to you. And if you have any more now, go ahead and put them in the question box. So I'm just going to go through with the questions, and then we were getting a lot of questions about access to or getting a certificate or CEUs and things like that. So Amber will be able to answer some of those questions as well. So I'll start with question 1. Does higher radiometric resolution lead to more noise? Is there a threshold beyond which noise starts to become a problem? So the short answer is yes. The higher radiometric resolution does lead to more noise. There's a sort of a fine line between noise and detail of information that you want to see on the ground. And so most people kind of in the remote sensing world prefer to have higher radiometric resolution and then deal with the noise at some point. And so, for example, when we do our land cover classification, if there's a lot of noise in the imagery, and typically if you do a pixel-based classification, there is a lot of noise. And then there are filters and things you could run over the imagery to deal with that noise. So in some ways, it's just better to have the higher radiometric resolution and then kind of deal with the noise in other ways using filters and things like that. So Amber is busily typing away, as you can see, so maybe I should slow down a little bit. Are the images, so the Landsat image that you used today already corrected for reflectance and so forth? The answer is yes. So we downloaded imagery from the USGS surface reflectance imagery. And I guess that's one thing we didn't really go over with you in the lecture. But yes, it's already been corrected atmospherically and radiometrically. Question 3, what false color is best for, so what basically color combination is best for showing surface water? my opinion is that any band combination that brings in the mid-infrared band, so that for the Landsat 8, it's band 6. For any of the other Landsats, it's band 5 and 7. Anytime you use that mid-infrared band in your band combination when you're viewing imagery, it will sort of enhance the water bodies because it is one of those bands that allows you to see more moisture, whether it's moisture in the soil or moisture in the vegetation or surface water. So that is the band combination I like to use to look at surface water. And question 4, we had several questions on this one. Is there a guide or quick sheet for band combinations that'll produce what we're looking for? So we've given you a couple links there that you can try out different band combinations. What we always tell people is that you use the band combination that you like the best or for the features that you're trying to bring out. I always like the ones with the mid-infrared band in. Other people like to look at vegetation as red, so they like the false color because sometimes you can distinguish between different vegetation types better if it's red. So it's definitely a personal preference, but there's a great list of the different band combinations in those resources, in those web links that we just listed. Another question 5, does the greenish tinge to some water bodies on the Northwest, and I'd have to go back and look at those specifically, indicate the presence of algae? Yes, it could. So generally, if you have if the water is either shallow, could be shallow, or and have a lot of sediment in it, or if there's algae or other kinds of vegetation in the water, then yes, it will also show up as green. That's a great question. All right, so I'm going to take a look at the chat and see if there's any other questions that come up. There's some questions about using ArcGIS Desktop versus Pro versus QGIS. So what you'll need to do if you're not using Pro is you'll need to look at those exercises that we've written up for ArcGIS Desktop or QGIS, because all of everything that we went through in this exercise today will be written for those software packages specifically. So here's another great question. Why is it that urban would be so high in NIR? It's actually urban, well, depending on the surface. So if you think about it, if you have a really bright surface like concrete, it will actually have a high value across the board, like in all band lengths. If you have something like concrete, which is black, if you look at it with your eyes, it's black, then it will probably be dark across the board. If it has any vegetation in it at all, so lots of times you'll have tree cover within urban areas, that's when you'll get that increase in near infrared, typically. So urban is really challenging because it has all of those different kinds of spectral characteristics. All right, and I know we're at the top of the hour now, and so we don't want to go on too much longer here. So Amber, I'm wondering if you can hop on and just talk about how, again, just remind everybody how to access the materials, the exercises, the data, when the recordings will be available, and then maybe a little something about the CEUs and their certificates of completion.
Yeah, of course. Thanks, Cindy. I have some notes here that I've been using for answering the questions regarding these things. So all of the materials for completing the exercises, the data, and also the PowerPoint presentation, all available on the course website. We're trying to upload these materials in far enough in advance for you all to download them prior to the live session. So the week 2 materials will be available soon as well. So you'll just need to download that entire zipped folder and then save all of those documents to your computer as you work through the exercises. Also, we will have the recording available from this session. The way that's going to work is there will be a link on the course website to view the recording via YouTube. And we will need to process this recording and get that uploaded. So give it about a week. We haven't quite done the upload process yet, so I'm not sure how long exactly it'll take, but we're hoping to have the recordings for each session available to view online within a week of each session. If you are then you can also complete the homework assignments. We've provided the link to the Google form. So all of the homework will be available via Google Forms. So you'll just need to complete the questions, upload some screenshots, doing that all online. We will have the link to each homework assignment also available on the course website soon. And all of those are due on November 30th. So you can complete them as you'd like, but it is really useful to complete those questions alongside actually going through the steps of the exercise because they relate to the steps of the exercise. So I would encourage you to sort of take a look at the homework, maybe have that open while you're working through the exercise as well. It'll just simplify your life in that way. And then in terms of the continuing education credits, those will be made available through our partner with the United Tribes Technical College. The handout for that document is available for download in the handouts tab of this webinar. It'll also be posted to the website. And if you could complete the form within the next week or so and email that to Anna Basson, and her email address is shown here. Actually, I think I'm still sharing my screen. And I've included all of this information in the chat as well. So do take a look at that for reference. And really, the main thing is just go back to the course website and check in on those items and that information. And then we'll be reminding you all through the each session as well where you can find those materials. And I did also want to note that we did have a lot of questions about ArcGIS Pro and Desktop and QGIS, and so you can use any 3 of those software systems to complete the course. All the exercise step-by-steps are available for each of those. We're only demonstrating in Pro, but if you have QGIS, you can still complete all the exercises, complete the homework, you can still get your continuing education credits. We just won't be demoing that through the actual sessions. So do please use whatever software you feel most comfortable with. And in terms of troubleshooting, downloading software, those types of things, Cindy and I might not be able to help with that very much, but there are some really great help resources and forums available. I know in particular for QGIS, if you're having issues downloading QGIS, they have a great help website and contact information there as well. So I think I covered most of that.
So with that, I think we will end the session for today. So hope you all have a great day, you guys, and we will talk to you again on Thursday.